Hi, thanks everybody. So I will, or after the previous talks have been more library-driven, the problems that I will present now are more application-driven from our perspective, developing a semi-Lagrangian solver for 6 dimensions. Just a few numbers. So what we're trying to do is processing 60 to 300 gigabyte for about 1 million steps. We accelerated our simulations by a factor of 3 to 5 and could actually reduce the resource usage by a factor of 10 to 50 by actually describing bottlenecks and saying, okay, please don't do this. So the physical background of this is similar to the DDC library, which was presented yesterday, that we would like to solve the Vlasov equation, which can be used to define the motion of magnetically confined plasmas. The model that we're currently using is still strongly simplified. It's an advection equation. The challenge here poses the 6-dimensional phase space. Lower dimensional models have been developed and proven successful, but the assumptions of these models are not necessarily valid in all regions of a fusion device. So the numerical method that we are looking into is the semi-Lagrangian method and combined with a splitting approach. So I simplified this for a 2D example here. We have an advection equation which we solve by splitting it into 2 successive 1D problems and then using the fact that the advection equation is volume preserving, so we can move back in time and interpolate to get a value of the distribution function at the current position. And we do this in separate stages. So first we interpolate on the x dimension by a shift using a Lagrange stencil, a Lagrange interpolation. And in the second step, when we go to the actually full time step, we interpolate on the y dimension with a Lagrange stencil. So this is basically a stencil algorithm that we're looking at with varying coefficients in the stencil. The discretization and domain decomposition is reasonably simple. We use a finite difference, a pointwise discretization, and a domain decomposed grid. We need to apply the stencil, a next neighbor communication for the interpolation. So we need to send halo regions from one point to another. And we need to do partial reductions to, for example, calculate the particle density. So in this case, we need to, for example, just reduce on V. So we need regions which share different V regions but the same X and do a reduction there. And then we want to work on these lower dimensional topologies as well. The software stack is the following. The library is called BSL6D for backward semi-Lagrangian in 6 dimensions. We use Kokkos for the parallel backend. So Kokkos, OpenMP, and HIP we have used. MPI to distribute actually our data, OpenPMD for I/O. HeFFT for the Fourier transform. We are actually looking, or we are hoping for some input maybe from Kokkos FFT to replace it at some point. And now let's have a look at how well our implementation performs on a simple use case, shared and distributed memory performance. So the first thing is that we actually have a memory problem in this setup. If we would go a direct way and allocate a 6-dimensional hypercube and include the halo regions into this hypercube, we would only or our compute region would only be about 50% of the memory that we actually allocated. These are the dashed lines here for stencils where we integrated the halo regions into the main computational domain. So this goes for a 5-point stencil only to about 50% if we consider a hypercube with 35 to 45 points, and that would already be 14 to 66 gigabytes, so in the range of some of the vendor GPUs at the moment. So we can't really use a single array to get or include everything into a single array, the halo regions. So we split the halo regions into separate arrays, and then we have the advantage, since we only do 1D advections, that we don't allocate the corners, and we can do we can share the memory of the halo regions between the different dimensions. How do we apply the stencil to this problem? That is a bit more tricky because we cannot just sweep through memory, which is not continuous any longer. This is illustrated here to the right side. We do 1D interpolation, so what we're doing, we're collapsing remaining dimensions into a team policy. Then we have a remaining interpolation dimension and a continuous dimension, and we allocate a 2D scratch space memory and use a team thread range and a team vector range to iterate through the continuous on the continuous dimension and the interpolation dimension, and copy that memory from the halo regions and the compute domain actually into a small 2D slice. And then we apply the stencil to the 2D slice and write the data back. So how well does that performs? The experiment setup is the following. We just look at one hypercube with 37 points in every direction. We interpolate in all 6 dimensions, measure the performance with NSide Compute, RockProf, and Liquid, and then evaluate it for an NVIDIA V100 and AMD 250, where we only used half of the GPU available, since it actually has 2 cores on it, basically, and an Intel Xenon Gold. And this is what we get there. So going from the Intel Xenon Gold to the NVIDIA V100 with the algorithm, we get an acceleration of a factor of 3.5 to 7.5. And going from the ME 250 to comparing the Intel to the ME 250, or half of it, we get a factor of 4 to 8. What we can see is with an increasing stride, we get fewer performance. So on the CPU, the V3 dimension is continuous in memory, and on the GPUs, the X1 dimension is continuous in memory. So we already get a nice speed up, or an okay-ish speed up. So how well do we utilize with our algorithm actually the capabilities of the given hardware? So we compared against the black lines, which are hardware specifications, and a simple Babel stream, which we compile and then run. And what we can see is on CPU, we can utilize the the given bandwidth quite well, since we are memory bound in our computation. Actually, the 90% I think is of an internal stream benchmark that we did, so that's not comparable to the vendor specification, but it's still quite okay. On the GPU, we still could try on more performance, since we are only getting about 50% of the peak bandwidth on the GPU. What we also looked into, how well does the caching works with this algorithm. The caching ratio, so at 1 we would have perfect caching, just reading and writing every value exactly once. On CPU this works again quite well. On AMD, which is in the middle, the values are not necessarily trustable, since we have values larger than 1, and we definitely don't read fewer data than we actually need. And on NVIDIA GPU, the caching ratio is at least 80%. So much for the distributed performance, for the shared memory performance. But now, before we actually optimize, we thought like, okay, we already get a speed up, so let's try to do some scaling and see how much we can go to larger scopes, since we actually want to get a higher resolution on the grid, or higher resolution simulations. And here we run into a severe problem. The experiment setup is the following. We do a weak scaling with 32 points in every direction. We parallelize one additional dimension in each of our weak scaling steps, and we compare the following runtimes, which are the interpolation stencil, the interpolation, the halo communication point-to-point, the reduction of n, and the solution of the field equation, which is a Fourier transformation. So the distributed memory performance looks at the following. In the optimal case, we would get a nice flat curve, which is unfortunately absolutely not what we see. the first thing that we can say is, okay, at least the lower dimensional problems are not problematic. So we see down here that is the reduction of the charge density and the Fourier transform, where we don't see a lot of impact. On the GPU, a similar behavior. The advection kernel, so the interpolation itself, also stays constant, which is to be expected since we do weak scaling. But now if we look at the communication, we see that it significantly increases and that we really don't get a good scaling in there due to the large difference between the on-node capabilities and the network capabilities. So on CPU, we can still at least parallelize 4 dimensions before we are fully compute bound, so we can go with 2 dimensions between different nodes, while on GPU, this is the local internal cluster. If we consider only 1 node, we actually get a severe problem and we're completely memory bound immediately, network bound immediately. And this just gets worse with every step. So we can take a look at the efficiency that we have for this and compare it to a simplified theoretical model. So for the interpolation time, we take the degrees of freedom divided by the memory bandwidth, and for the halo time, we take the degrees of freedom that we actually communicate and divide by the maximum peak network bandwidth. And for a CPU, we have the green lines here on the left side, which works quite well, or which matches. And on GPU, the light blue theoretical line is even worse, but since we don't actually get the peak performance of the memory on GPU, we correct that, and if we compare it with the memory performance that we actually measure on GPU, we get an efficiency of, if we parallelize all dimensions, only 10% left. On the right side, we have, again, a GPU example, just comparing against the stronger network, which was Joule's booster. So, well, there we obviously get a slightly better efficiency, but we see the same problem in there. So this is a severe problem that we will have to look into, and I'm a bit curious whether more numerical methods will run into scaling problems if the network and the on-node bandwidth actually will differ further. And now really more a wish list or for resource managed communicators. Maybe that's a personal thing, but I'm really not a great fan of global states in code, so it would be nice if I could actually bind the lifetime of the communicator to the distributed object. And also it would be nice if it would be easier to utilize communicators and in the scope where I actually need them, because with a 6-dimensional domain we actually get quite a lot of different communicators which are available. We need the full communicator for point-to-point communication. We need the particle reduction, which only reduces on the velocity domain, so does not communicate between X domains. Then we have the Fourier transform, which only is on the X domain. Then we have the partial average. We have another algorithm which only partially averages the density. So that would only require that 2 X dimensions actually may not communicate, while every other dimensions are reduced. And in total, we would have 63 communicators per particle species to actually get all the reduction combinations that we have. And if we then add a new particle species, we would need another set of communicators to actually distribute this. So a really simplified approach could be to use resource-managed communicators. And, well, this is definitely nothing that should be used yet in a global state, but it's a suggestion that trying to wrap a communicator into some kind of resource-managed object that goes out of scope. It actually frees the communicator again. I need to think less about it. One question that was raised, this is a really simplified example, which we just tried briefly. How expensive is it actually if we don't know how many or how often we allocate and deallocate communicators? We did a simple example, creating 1,000 communicators with OpenMPI, sending a small message and freeing the communicators, and apparently only creating the communicators was expensive enough to measure something. So if we want to bind the lifetime of a communicator, what kind of cost should we think about in terms of runtime? This is, again, a simple scaling going on from a single node to multiple nodes, from 2 to 64 processes, and creating a communicator on a single node with one process is actually still pretty cheap, so we wouldn't worry about this in the low case, but if we actually want to scale, this might become expensive. So comparing to what we have, for example, in the interpolation, creating a communicator versus the interpolation on a CPU would be a factor of 1 to 100, while on GPU, creating a communicator or doing the interpolation is 10 times as expensive as creating a communicator, so there it might be a bit problematic to create and destroy communicators too often. With this, I'm actually already through my presentation. So the summary would be we implemented a solver for the Vlasov system with a single kinetic 60 species. We have, well, let's say, sufficient utilization so far on GPU and CPU for our prefetching algorithm. We classified quite extensively communication bottleneck between internode communication or internode communication, and we provided some kind of motivation of resource-managed communicators to reduce the overhead on application developers in that sense. And the outlook would then be reducing internode communication through, for example, exploiting that in a different coordinate system, particles move slower, so we might need to communicate less and do a bit extrapolation and do a few more interpolation steps in between. Higher dimensional interpolation stencils would be interesting for the Vlasov equation so that we don't do 1D interpolation but higher dimensional and multi-species simulation. And with this, thanks. And
thank you. Any question?
So you have 3 dimension in space and 3 dimension in velocity, right?
Yeah.
Okay.
Plus the species. Sorry? Plus the species. Plus time.
Species.
Plus species. Yeah, but at the moment we just have one species and the problem. So it's a really simplified physical model.
What is exactly the situation you think the gyrokinetic is insufficient, and also Lagrange interpolation is always good enough for you?
Oh, that's probably more a question for a real physicist working on magnetic fusion devices. As far as I know, the assumptions for gyrokinetic theory are valid for slowly varying gradients in temperature. And if you go to the edge of a fusion device like a tokamak, these assumptions are not necessarily valid, so that the temperature gradient is actually at the scale of the Larmor radius, so that you need to consider kinetic effects in this problem. So gyrokinetic might not have valid assumptions at that point.
Mark?
Yeah, good talk. Thank you. I understand what you mean now by resource-managed communicators. And to me, that says that you actually have tasks and you want to express that some tasks are independent. And you're stuck with this medium of MPI communicators that can be quite expensive to create and destroy. And maybe there's a mismatch to your programming model there.
Okay.
Yeah. So,
that could
yeah,
be.
thank you.
All right. Thanks again.